Jai Hind. The topic which I am going to discuss today is classical problem of synchronization, and it is a part of unit 2. Classical problems of synchronization which I am going to discuss today. The first one is the producer consumer problem. Then we will see what is readers writers problem, and the last one is dining philosophers problem. First we see that what these problems mean, and after it, that is how we are designing the solutions for these problems. And basically we are going to see the solution today with the help of semaphores. So basically, what is a producer consumer problem? In the case of producer consumer problem, we are having a shared array or a shared buffer. This is the shared data. One process is acting as a producer and other process is acting as a consumer. So what is the meaning of producer and consumer here? Producer is writing something to this array or to this buffer, and consumer is only consuming the items. That is, producer is performing write operation on this array and consumer is performing only read operation on this array. So producer and consumer, they are executing concurrently, but only one should be using the buffer at a time. Now what will happen if both these processes, they are trying to access this buffer concurrently or simultaneously? Then in that case, there may be the possibility that the consumer is reading the data or producer is writing the data in such a location which makes the data inconsistent. So producer is putting the item to the buffer but should not be allowed to put the items into a full buffer. That is the condition we need to check. That is, if this array or if this buffer is full, then producer cannot write or perform write operation on this buffer. Whereas in the case of the consumer, if the buffer is empty, then in that case, the consumer is denied to read something from the buffer. So consumer, it consumes the items from the buffer but cannot remove the info from an empty buffer. So in this case, what we are having two operations. One is there is a competition between the two, and another one, the cooperation between the two. They are competing. They are competing on what? The producer and the consumer, they do not access the buffer area and related variables at the same time. This we need to check. Cooperation, that is, no item is made available to the consumer if all the buffer slots are empty, and the no slot in the buffer is made available to the producer if all the buffer slots are full. In this case, we require a cooperation between producer and consumer, and in the first case, that is when there is a competition for the among these two, producer and the consumer, for the same shared buffer, then in that case we need a mechanism with the help of which we will see that only one process should be active in the buffer. Now how we are designing the solution for the competition as well as for the cooperation. So what we are having n buffers. This is shared between the two processes. Then we are using 3 semaphores. One is mutex, which is initialized to 1. This is basically we are using for the competition part, to handle the competition part, and these two basically we are using to handle the cooperation part. So semaphore full, it is initialized to value 0, and empty, it is initialized to value n. So in so what the full is doing, full is seeing whether the your array is full, is empty or not, and with the help of empty we are seeing whether the buffer is full or not. Now this is the structure of the producer process. We are first we have used the do while loop. This is a producer. It wants to produce something into the buffer, and this is a critical section of our code where we want to access the shared data item. This is basically we are checking for the overflow condition, and this is basically we are using that only one process should be active in the critical section, that is your entry section. Similarly, with the help of the signal operation, first we are notifying the other process that if you want to access the buffer, now you can do so. And with the help of signal full, we it is the again the notification to the consumer process that now there is some item in the buffer, and the consumer can go for reading that particular item. So here we are aware that we have initialized empty with the value of m and full with the value of 0. So what we are doing in this, we had applied the wait operation on the empty semaphore. Now the empty semaphore value is n. So this means that now the producer process can produce something. There is no overflow condition. When the overflow will happen, when this empty value becomes 0, because at that time all the slots are full. So this is how we are handling the overflow condition with the help of a semaphore. Now in this case, initially we are having n slots, which signify these n slots are empty. So now the producer process, it can go for producing the item. When it start producing the item, it will again lock the mutex value, that is a mutual exclusion. Now this will become 0 when this operation is successfully operated, successfully executed. Now this process will add the item to the buffer. After adding, it will signal the mutex. That is again the mutex value will turn to 1. Now it is a signal to the consumer. Now it can go for removing the item from the buffer. And signal full, initially what is the value of full? It is 0. Now it will become 1. That is one item has been produced in the buffer. Now this is the code for the consumer process. First we are doing the underflow checking in this case. And how we are checking the underflow? That is again with the help of full. Initially, let's suppose that the before going to the producer process, the context switching happens, and your CPU, it starts executing the consumer process. Now at that time, what is the value of full? It is initialized to 0. There is no item in the in your buffer. Now in this case, since we had applied the wait operation, now this consumer process will stuck in this wait operation and it will not move further. Now what will happen after this? Here, as soon as the first item has been produced, that is full becomes 1. Now this will come out of the wait operation and it will move to this wait mutex. And we have seen earlier its value has been updated to 1. When it moves to its critical section, it will remove an item from the buffer. As soon as it comes out its critical section, it will notify the producer process that now it can again start producing the things, and it will again do so with the help of mutex, because here after this operation, execution of this operation, its value has become to 0. Once it has been signaled, again its value becomes to 1 and it will do signal empty. Now one slot becomes empty. So here what had happened? Empty, that is here we are n. When this has been executed, its value becomes n minus 1. When this executes, again this value becomes n, because the producer has produced one item and the consumer has consumed one item. So again the value becomes n in this case. Another problem is the readers writers problem. Here the data set is shared among a number of concurrent processes. What in the case of the producer consumer, we are having one process acting as a producer, another process is acting as a consumer. But what is happening here? We are having a set of processes which are termed as readers and a set of processes which are termed as writers. In the case of the readers, they can only perform the reading operation and they don't perform any update. Whereas in the case of the writers, they can go for both. That is, they can go for the reading as well as writing part on the shared data set. So now what's the problem in this case? In this case, allow multiple readers to read at the same time. That is, we are aware that if 4 processes, they are reading the database, then your database doesn't go into the inconsistent state and no race conditions would be arising in the case of multiple reading. But as soon as one process start writing, then no other writer process and no other reader process should be allowed to access the data set. So only one single writer can access the shared data at the same time. So this is the problem in this case. That is, we are having a data set, we are having readers, we are having writers. When reader are working on this, at that time writer is not allowed and multiple readers, they can go for the reading part. But as soon as any one of the writer it got access to the data set, then no reader and no other writer is allowed to allowed to work on this data set. So we have to synchronize their actions. How we are synchronizing their actions? That is with the help of the shared data, the data set which you need to operate upon. Then we are having a semaphore mutex again for the mutual exclusion, and it is initialized to 1. We need another semaphore, that is WRT, which is again initialized to 1. And there is another variable, that is a read count variable, which is initialized to 0. With the help of this variable, we are keeping a track, that is how many reader process at any time is active or working on that particular, on the shared data set. So this is the structure for the writer process. In the case of the writer, this is entries, this is our entry section, this is our critical section, and this is our exit section. So critical section code, it could be any depending upon my application. But in the entry section, what we are doing, we had applied the wait operation or use the wait operation of the semaphore with respect to WRT semaphore, and as soon as the process, writer process, it comes out of its critical section, it will send signal to other processes with the help of this exit section code. So initially, as we have seen, initially WRT is initialized to 1. So if the scheduler, it selects the writer process first, then in that case, it will execute this, WRT value becomes 0, it will move to its critical section. Now, if another writer process, it wants to access the data set, then it will deny the access, because here now the WRT value becomes 0. So, the second writer process is not allowed to enter into the critical section. So we have achieved the synchronization or the order between the two writer processes. As soon as it comes out of the critical section, again the WRT value becomes 1, and the second writer process, which is in the waiting state, now it will move to the critical section. This is the code for reader process. First, when the first reader process, it wants to enter into the critical section. This is the critical section part. So what we need to do, we have to increment the read count variable by 1. Now what is happening? Other read count, suppose second reader, it comes again, it will increment the read count variable by 1. Now both the processes, first reader and the second reader process, they are trying to work on the same variable. So there may be the chances of race conditions in this case. So in order to avoid the race condition, we need to synchronize the action on this. So this becomes another critical section of your code. And since we need to synchronize the actions, so we had used this wait mutex. First, we need to go for the wait mutex. It will do the read count plus plus, and after that, if reader count is equals to 1, then we are waiting. We will go for this operation. What is happening here? For the read count, this is how we are handling this part. If the mutex initially, what is the mutex value? Initially the mutex value, it has been initialized to 1. So when the first reader process comes, the mutex value becomes 0 when this instruction is successfully executed, and this read count variable, it becomes 1 in this case. Now it will check here. If this is the first reader process, then it need to check, is there any writer process already working on the data set? And for this, we need to apply this operation, because we have already seen if one writer process is operating, then no reader and no another writer process should be allowed. So we have seen how to synchronize the action between the two writer process. Now with the help of this, we are synchronizing the action between the reader, that is the first reader, and the writer process. Now in this case, if this is equals to 1, that is the first reader process, then we will check the WRT. If the writer process is not working, then in that case WRT is 1. If it is successfully executed, automatically this value becomes 0. Now if this WRT, it try to go into its critical section, it will find its value 0 and it has to wait until the reader process again send the signal as a to the WRT semaphore. After updating this variable, it will send a signal to other reader process, that is now you can update the read count variable with the help of this statement. It is sending a signal. Now the first reader, it will perform the reading operation, and after completing the reading operation, again the read count variable need to be decremented by 1. So again, to avoid the race condition, we have to synchronize the actions between the reader processes. That is, no two reader process should work or should access the read count variable concurrently or simultaneously. So how we have done? Again, we have used the wait mutex, and to notify other reader process, we have used the signal mutex. But what is the significance of this statement? If read count is equals to 0, that is, if the this is AD. If the read count variable is equals to 0, that is, it is a last reader to perform the reading operation, then it need to send a signal to the writer process. That is, if some other writer process is waiting to go for the go for writing part, then they could do so. After sending the signal to the writer process, it will send the signal to the reader process. This is for writer process, and this is for other reader processes. So this is how the reader process works. And this is how we have done the synchronization between readers and between readers, writers, and among the writers. So if you look here, we are having a writer process. Here we are performing the writing operation, and in this case, what is happening? We are having the reader process. For read count, we had deployed this, and for this decrement, we have applied PND. So what will happen? In this case, starvation is possible for the writer process because everything is depending upon this. So what happens if first reader process starts reading the data, then it is allowing the other reader process. Now the reader process, they are coming again and again. So your writer process, it might go under the starvation stage. Another important classical problem is Dunning-Philosopher problem. In this case, we are having a shared data set. This is the shared data set that is depicted with the help of a bowl of rice. We are having 5 philosophers who are sitting on these 5 chairs. So initially, I could assume these philosophers, they are my 5 processes. And this is my shared data set among these processes. But in the case of Dunning-Philosopher problem, the philosophers, they are allowed to do only 3 activities. That is, either they are thinking, or they are eating, or they are sitting idle. So here we are having that is how they are eating the rice. They need to get access of these 2 chopsticks on their left and on their right side. If they are able to grab both the chopstick, only then they are allowed to eat the rice. So in this case, we are having a set of processes, 5 processes, a data set, and these processes, they are allowed to work on this data set only if they satisfy the constraints which has been kept in that particular problem. So in this case, what is that constraint? That constraint has been applied with the help of these 2 chopsticks. So we are having 5 philosophers sharing a common circular table. There are 5 chopsticks and a bowl of rice in the middle. When a philosopher gets hungry, he tries to pick up the closest chopstick, that is their right and left side. A philosopher may pick up only 1 chopstick at a time and cannot pick up a chopstick which is already in use. When they finish eating the rice, they need to put it down so that other process or philosopher who is in the waiting queue, they can use that chopstick. So in this case, the shared data is a bowl of rice, that is a data set, and how we had applied the order among these philosophers or processes with the help of an array of semaphores by the name chopstick. Since we are having 5 philosophers, so we require the length of the array is going to be 5. and this array has been initialized basically with 1. So this is the structure of philosopher I. So here it is the eating part, that is a critical section, and this is my entry section, and this is my exit section, and this is remainder section. So before entering into the critical section, the code of entry section need to be executed successfully. Similarly, when the this critical section code it executed completely, then this particular code need to be executed, that is our exit part. So in the entry section, we are checking for both the chopsticks, immediate chopsticks, that is on the left and the right. Since this is a circular table, so that is why the array has been implemented with the help of circular array. So first we need to check the chopstick for the right. Suppose this is I, then automatically this is your circular array. So this will become I plus 1 mod 5. This is how you will identify the index of the next chopstick in the case of a circular array. Now first it will check for this. If it is down, then it will pick up. After pickup, it will update its value to 0 so that this philosopher won't be able to use this. It will go in the waitings mode. Similarly, after picking this, it will check for this chopstick. If it is free, then it will pick this chopstick and go for the eating part. So here we have checked with the help of wait operations. Similarly, when it finish eating, it need to put it down, and how this operation being reflected with the help of signal chopstick I and the signal chopstick another value, that is I plus 1 mod 5. This is the solution with the help of semaphores for the dining philosopher problem. These are the references which I have used to discuss this topic. So in this particular lecture, we had discussed 3 main classical problems. One is readers writers, another one is producer consumer, and the last one is dining philosopher problem. We have seen the solution with the help of semaphores. So this is all about for today. Thank you and Jai Hind.